And what the perfect timing it has been, like 2-3 days back. So we got the news that two physicists, Peter Higgs and Francois Riga, they shared the Nobel Prize for theoretically discovering the mechanism which helps us in understanding the origin of Mars. And it has been experimentally verified by ATLAS and the CMS experiment last year with the discovery of the Higgs boson, which is the missing particle, which has been predicted by their theory, named after the Nobel Prize winner Peter Higgs. And since CSU is the only campus which has been involved in the CERN experiment, so and we feel very proud and privileged to be a part of that ATLAS experiment, and to provide the opportunity to the students for the other CSU campuses. So their effort has been going on to make this a CSU-wide consortium, and already we have 14 CSU campuses involved in this. And this year, the 2 students from Channel Island and the 3 from the Fresno State students, they got the opportunity to work at CERN. So today they will be giving the overview of their work, and they share their experience. So to start with, I invite Brendan. So
do I need the mic, or can you hear me? Or?
I think Mike.
You go to the mic. How's that? Can you hear me?
Very good.
Okay, awesome. Actually, make this happen. Okay. I should have changed that on the title. There's the laser here. There we go. Oh, this is great. Okay. Hi, everybody. I'm Braden. I'm going to introduce kind of what we're doing at our what we did at Atlas, and kind of what Atlas is, what CERN is, the LHC, the Large Hadron Collider. This was my title page from another colloquium, so I forgot to change that one title. So forgive that, but everything else should be accurate. Let me go over what is CERN, what is Atlas, kind of talk about our experiences at CERN. You're going to hear more about what we all did. Simon and I worked together, so he's going to go over what he and I did over the summer, and then you'll also hear from the other guys. We also had some experience in Europe. You're going to see a couple of pictures of that throughout the hour, and then also have some information on how to apply if you're interested in doing this. So the question to start out with, what is CERN? CERN is I think of it as a pseudo-acronym for the European Organization for Nuclear Research. It is the world's most prestigious scientific institution. We have 8 Nobel Prizes now. It's also the birth of the World Wide Web. This gentleman right here invented the World Wide Web and asked CERN to give it to the world for free, and they did. And it's located in Geneva, Switzerland, which is a very nice place. Most recent major discovery was the Higgs boson. It was announced July 4th of last year, and that they had discovered the Higgs boson. And just a few days ago, Peter Higgs and there's the other name, Francois Englert, were given the Nobel Prize 2013, Nobel Prize in Physics for proof of this discovery, or for this theoretical discovery. So those are the big news that just happened a couple days ago. And of course, the Higgs boson, the big question is, why do we have mass? Because we can't exist without mass. We wouldn't exist without mass, and the Higgs boson explains how that happens. CERN itself is, and the picture's a little hard to see. I tried highlighting it. This green border right here, that green line, that's the border between Switzerland and France. It's and if you look on the bottom right there, that's the Geneva airport. This will give you kind of an idea as to how big it is. It's 17 miles long. This red ring right here, that is the accelerator. It's cost $10 billion to build. Over 10,000 scientists from more than 600 institutions and over 100 countries are working at CERN. One of the 4 major experiments that's happening at CERN is the ATLAS experiment. It's one of the big colliders, or one of the big detectors. How big is it? Well, it's 85 feet in diameter. It's the height of a 6-story building. If you see right here, that is a person. There's a person right there. There's a couple of people right there, just to kind of give you an idea of the scale of this thing. And of those 10,000 scientists at CERN, 3,000 of them alone work on the ATLAS experiment. This is one of the big flagship experiments of CERN, at CERN. But ATLAS doesn't just happen at CERN. It's a worldwide collaboration. We have international labs, Canada, Italy, France, Germany, Japan, Russia, China. We also have international universities, big name universities, Cambridge, Oxford, and US labs, Argonne, Brookhaven, Lawrence Berkeley, Stanford, and as well as big name US universities, all working together on this one collaboration to detect all these particles. Fresno State is the only CSU working at ATLAS. We're funded by grants from the National Science Foundation, 2 major grants, and that's for the research is what it's funding.
So what, you and Simon have a big smile on your face right here? You and Simon have a big smile.
Yeah. I think we're the happiest to be there.
There you go.
The other guys were like, they're like, what is this place? They told me there'd be donuts. So that was actually, that was our trip. We actually got to go down into the Atlas Cavern. It's 100 meters underground, and got good pictures of us down there. It was a lot of fun. I think that was probably the coolest place to visit because nobody ever gets to go down there. So, since Fresno State is at Atlas, doing work at Atlas, there's this outreach to all the CSUs, the CSU Nuclear and Particle Physics Consortium, which is 14 of the 23 universities in the California State University system. And these 14 campuses, I have them listed out there, we've sent 24 students since 2008 out to CERN. And we've worked with top scientists in the field, which is really, really cool stuff. There's some of the pictures. I think these are the last 4 years of all of us going out. It's the Atlas Tunnel. Same one here. This is outside the big dome. And there's the other one outside. There's some of the old accelerator columns out there. So we've sent 24 students. The CSU has sent 24 of the top students, really their top STEM students out to CERN since 2008, and it's been a really great experience. This past summer, of course, the first 3 of us from CSU Channel Islands just joined on to the new pack. It was myself, Cameron, and Graydon. You'll hear from both of them today. I'm actually now here at Fresno State, so that was my last thing at Channel Islands. And now I'm here again. So that was our first 3 that we sent down there. Now at CERN, to get to CERN, part of this application, part of the whole getting in there thing is we have to take these high energy physics courses, programming and root courses. We also have an application, a whole application process I'll talk about towards the end of my talk here. We had to take these classes online. We had to do well, of course, and that was probably the big thing for preparation. What we got was 10 weeks in Geneva. We got to work alongside the world's top physicists, engineers, computer scientists. We got to do real research. This is me and Simon working, and this is an actual detector. I think we were taking it apart at that point. But we got to do real research, working on the actual hardware. I got a picture of Jimmy and a picture of Simon, or Graydon, mixing everybody up now. Doing work. You'll hear about what they got to do. Our work was, we actually contributed to the Atlas experiment. We were actually a part of this, and our research was actually beneficial to the Atlas experiment, and so we get to present to the Atlas working groups. These are the top scientists in the field that are interested in what we're doing, how we're making a contribution towards, what we learn and how it helps, building. We're in the middle of upgrades right now. One other cool thing that we got to do is there's a summer student lecture series. Every day, 5 days a week, we got to attend the student summer lecture series. These are lectures on the most advanced topics in physics, data acquisition, sensor engineering, all sorts of other things. I can't even remember all of them off the top of my head, but it was a great lecture series. We got to do it every day. There's 3 lectures, and these were the top scientists in each of these fields talking about the most recent discoveries, the most recent construction, everything that's most recent in each of these fields. That was fantastic. And of course, we also got to do some traveling. That's what we get to do on the weekends. We have Venice here, and this one, I can't remember where that was. So yeah, we got to travel around in Europe a little bit, which was great too. A wonderful experience. My first time out of the country, actually, so it was quite amazing. So I just really wanted to just bring it home. This is the most advanced science in the world. Computing, engineering, it's the most advanced in the world. Building such a huge detector and making it work perfectly and flawlessly takes a lot. And so we've been, and this is what we're part of. CSU students actually being a part of something so, worldwide, such a worldwide importance. We also got to learn the hardware. We got to learn the software. We got to create. We learned how the Atlas experiment works. We got to even visit the detector. We got to collaborate with top scientists in the field. We got to do fundamental research. And then, of course, we also got to do the summer student lecture series. So for anybody who is interested, this is what is necessary. This website here, Dr. Gao has a website that has all the information on it. Very important, the application does have to be in by February 1st. If you are interested, it has to be absolutely, everything has to be in, not just the application, even your letters of references, even your transcripts, everything has to be in by February 1st. So we have the programming classes, the application, cover letter and CV, references, and your transcript. All of that information is there on the website, and if you want, I can give you the website later if anybody's interested. So I just want to kind of give a preview as to what all you're going to be hearing today. So I kind of put it in here. I just gave you an introduction to CERN and the Atlas experiment, so we know a little bit about what it is. Simon's going to talk about the Micromegas mu1 detector upgrade, stuff that he and I worked on. Graydon worked on physics from the Atlas data. You'll have more information on that from the actual Atlas data. I actually just kind of gleaned that from your PowerPoint. Cameron worked on event generators, and Jimmy worked on top quark reconstruction. Quarks are very important in particles, if you know what they are. They make up mesons and bosons. And then lastly, I just want to throw in a thanks to our advisors at CERN, our sponsors at Channel Islands and Fresno State, everybody that supported us in this experience. And then special thanks to Dr. Gao, who's put this whole thing together. CSU Channel Islands, Dr. Doherty is the department head at Channel Islands. He did a lot of legwork for us. Same with Dr. Avona and the CSU Channel Islands IRA committee. They helped us out as well. Oh, that's that. And then who's next? Simon.
You guys read about
yes.
those talks you guys attended. Was that just students or everybody attended those talks?
It was just students.
Okay.
It was just students. There was, anybody can attend, anybody
Right.
who can actually get into CERN can attend, but it was primarily students.
Was it leading edge stuff you were doing there, right at the,
The talks,
right, was it about stuff like
Yeah.
you were doing right then, I mean,
Yeah.
up-to-date stuff?
and it wasn't just the stuff happening at CERN, it was the stuff that was happening
Right,
at all of the,
right.
collaboration,
Collaboration.
yeah. So it was
Because books we read is very, like, it doesn't contain the latest information, but the talks over there,
Yeah,
I think they are.
That's pretty nice to be able to do that.
Oh, yeah.
Get that in, so.
Yeah, the people that are elbow
But some of them will end up being wrong too, right? You know,
Yeah.
that happens,
Yeah, that does happen.
Exactly, it does.
Yeah. Okay, so I guess we can say questions, more questions till the end, so we can, we have time. Okay. Hello.
I probably will knock this off while I'm talking, just because my hands will be moving around so much. Let's see. I'll just put my pocket. Okay. So just like Brandon said, I'll be talking about the Atlas experiments and the upgrade that was that is going to be performed on it. Again, I'm Simon Gonzalez. I'm a physics graduate student here at Fresno State, and I will be presenting more stuff about CERN. Okay, so here it is again, that picture of the Atlas experiment. Again, it's a very large experiment. Brandon just told you it's 6 stories tall. So think of like Peter Business Building, which I think is 5 stories, right? Add another story to it. It's that high up. And it's just this massive device that they just threw under the French-Swiss border, about 100 meters underground. And again, that's a little person right there about my height, so just to give you a good idea of how big it is. And you see all this stuff in blue on the Atlas experiment. All of those blue panels are muon detectors. And as you can see, it just covers this device. It's just filled with muon detectors. So you're like wondering, well, why does it have so many muon detectors? Why do they want to look at this specific particle? What makes it so important? Well, muons come out of, there's a lot of muons that come out of collisions from these hadron beams. When they collide, it spews out a whole bunch of particles. Muons is one of the particles that it gives out the most. And it's a very detectable particle. It's 2,000 times as massive as an electron. It's quite easy to see. It doesn't live, it has a very short lifetime, but for the distances it has to travel and its velocities it's gonna pass through one of our detectors well in advance before it decays. And so another thing you might wonder, well, okay, sure, we can see these particles, but what's so important about this muon? What else could it tell us? Well, recently, as it was just told in the previous presentation, they found the Higgs boson last year, July 4th of 2012. And it was, I believe, Peter Higgs and his colleague got the Nobel Prize recently, and such a big deal for particle physics. It completes another part of that puzzle for the standard model. It still leaves a lot of questions open, but we're just adding extra parts to it. in order to explain it. But here we have a collision that is supposed to be much like the Higgs boson, a decay of 4 muons. And you can see these tracks, these red tracks right there, that would be the path of these 4 muons that is resulted from this decay from the Higgs boson. And that's data from the Atlas experiment from some time ago, from last year. So currently they do have a muon detector. It's been working and it's working fine. And it's made up of these type of panels that you have here. We're going to be changing that design. They're going to go from what they currently have on here, which is a monitored drift tube. Think of straws, right? And you have this nice thin copper line going through them, and it's filled with the gas. And this muon will pass through it, and it'll probably collide with some of the gas it has in there. And then you'll have this detection of the particle. It'll give you where it came from, its energies, important stuff in order to analyze what happened from the collisions. So they're going to swap those parts out and they're going to replace it with something much more efficient. They're going to get better muon detectors on there. So, and they want all these numbers on here. They want it to be a lot more efficient. They want it to be able to detect a lot more of these particles, make it much more luminous, make it more like detect more of these particles when they pass through it. So make more use of this area that you have filled with detectors, actually have more of these particles being detected, not just every so often. But it still detects quite a bit. Something that I left out on the previous slide is the Atlas experiment, it has a lot of data. Whenever there's a collision, it gets so much data. It's massive amounts of data. And the figures for that is about 1 petabyte per second for every time we have these events occurring. To give you an idea of what 1 petabyte is, I did a Wikipedia search for this a little while ago, and I found out that you could have the entire population of the United States, you could get their DNA and store it, and even store the DNA for their clones. So all that information that's required for all that DNA that makes you up can be stored, backed up, and then copied over again. Another idea for those of you that listen to a lot of music, MP3 files, about a 4-minute long MP3 file would take you could put up about 2,000 or 200 years, 2,000 years worth of music. So that'll give you another better idea of what a petabyte is. But yeah, the newer detectors are going to be much more efficient. They want these better detectors. And what are they going to replace them with? That's the work that we did. These micro-mega chambers. So they're going to swap these straw detectors out. They're going to put in these micro-mega chambers. And pretty much here we have a construction of one of these chambers, a wedge, just a small wedge. It's going to have four of these chambers on this wedge, and there'll be about 8 active layers in order to see, these collisions. And they're going to put them one over the other, so there'll be one in the front, one in the back, and they're going to arrange them in this wheel kind of formation. So they'll have them overlapping as well. And they call this small wheel right there. That right there's a small wheel for the Atlas experiment. And again, you can see how big a person is to the arrangement of these detectors. Okay, so what is a micro-mega? What does it do? So imagine a particle, let's say a photon, passes through here. Well, it's going to collide with some of this gas. It's going to ionize in. The electron's going to get dislodged because it's such a high energy particle. It'll dislodge that electron. It'll drift down here, passing this mesh area. Well, then an avalanche of particles occurs there. This whole avalanche of electrons fall from there, and it hits those resistors, those strips right there, and you gain data. You get to see, again, what was the energy of this particle, where did it come from, and this should be a much more efficient design than what they currently have. So to talk about the work that myself and Brandon did while we were there, here's the setup for our detector that we had. Here it is laying on a table, much the size of this, but something much more stable on a surface that wouldn't move. And we set up this digital dial gauge to take measurements of the surface. So we're just looking at the surface to see how smooth, how plain it is, to see how well these detectors were made. They're shooting for a certain requirement. They want to make sure when they take measurements for this, they get a standard deviation of about 50 microns. Currently, with the ones that they have, I had measurements from about 50 to 100. So not quite there, but they're getting there. And they still have plenty of time to redesign these detectors because they're not working perfectly. They're still in the design phase. And here's some data, and you can just see it overlapping on itself to see how smooth it is and how it compares with its own relative readings across the surface of this detector. Other tests we did was pressurizing these detectors. So we filled them up with the gas, and we saw how they just bulged, how they deformed. And we took measurements of the surface. Again, there's our surface of the detector, and this is looking at the top part of the detector. You see how much it deforms, and you see a greater deformation at the center when it's pressurized at 8 millibars. And then at the bottom, you see it deform again at the center. The difference here is of about 3 millimeters, a deformation of about 3 millimeters for the top and 5 for the bottom. And if you just look at one spot and look at its deformation in just one little spot, looking at the center, you can see how much it deforms from 8 millibars going all the way back down to 0. So starting from 0, pressurize that guy back up, you see how it deforms and by how much. Again, you got the top not deforming as much as the bottom. So in summary, all this work that we did with the Atlas Micromegas working group there at CERN. They're the ones that are creating these new detectors, these new muon detectors. And the work that we did there was a team effort by myself and Brandon. And we also had one more person working there along with us. She was from the University of Malta. Her name is Marielle Horgan. You see her there assisting me doing these gas leak detections. The work that we did there was also presented in a working group meeting there at CERN. We, myself and Brandon, both gave individual talks about the work that we did there to this group. And that's a real honor right there, a real privilege to be able to talk to these people that are just experts in this field. And they give us the opportunity to show us the results show them the results that we have gathered from our measurements. And it's important too because there's no models for these experiments. This is all brand new stuff. They don't have this is what they're shooting for, but this isn't the designs for how it's going to behave. They don't know how it's going to behave. That's why they had us there to see what happens when they get pressurized. Other things we did we did other measurements with that large muon detector. We did deflection tests, sag tests, a whole bunch of other tests because they haven't done that many tests on them. And we also took measurements of these panels, which they place the detectors on, so to see how smooth these panels are, either panels that they themselves make, or they order in from other manufacturers to see, hey, what's a good stable surface to place our detectors on. And also, we get to hear lectures. Great lectures, fun lectures. To name some of the ones that I enjoyed the most while I was there was some lectures on cosmology, antimatter, and astrophysics. And presented by experts from around the world, not just people that work at CERN, but people from Europe and the United States and other places of the world. They just bring them in and they're happy to talk to us and explain to us their field of research. So again, I would like to thank those who made this possible, the school, Dr. Gap, and all of those that make this program possible. And just to show you guys what else you get from going to CERN, you get to do a little bit of traveling. So that's CERN itself, and that came from an image that I like to call CERN at night. And you get to see some older experiments. You see them in the background. This is in Geneva, so you got Geneva right down the street from you. Go swimming there in the big lake that they have. You can also travel to some of the nearby cities. This is Neon. I did a 40-mile bike ride there. It was 40 miles round trip going there. And a little small city called Annecy, where they hosted the 20th stage of the Tour de France. So I got to check that out. And then we have these places here. Yeah, the Colloquium, right? So thumbs up and live, thumbs down and die, no, Russell Crowe. And then the Louvre in France, that big pyramid behind me. Thank you so much. And questions, yes?
What is the optimal resolution to the vectors and the efficiencies?
So they're shooting, yeah, so for the new ones that they want, they're shooting for increased luminosities for these detectors.
Some kind of time resolution too.
Yeah, let me go back to that slide.
And time resolution.
Yes, there we go. And that's what they're shooting for these newer detectors. The efficiency to increase by 98%.
But what are the current efficiency and practice?
98% from what they currently have now.
All from what they could.
Yes, yes. Yeah, so they're just using the specs that we currently have now. This is how much more better we do. What are the numbers for those?
Yeah.
I don't know those off the top of my head. I had to look them up. But yeah.
The thing was, you guys weren't working on mock-ups, you're working on the actual panel size and the wheel size of the panel, or is that mock-up?
That was already a functional detector. So we were just working on just the physical aspects of it, how well it behaves under certain pressures, under certain weights. But it was already ready to measure trapped particles. And they were doing that with cosmic rays. Unfortunately, when we were there, they had the LHC was down, so they couldn't use test beams. So they had to use cosmics, and that takes a while.
That's free.
It's free, yeah.
That's free, that's free.
Yeah. If you guys have any other questions, maybe we could say
Do you know when they will start the new phase, change the detectors?
ours is supposed to go in around 2018 for when the next time they shut it.
Oh.
Yeah, that's the goal.
You can go back to get perfect detectors like that.
Perfect. Yeah, actually have a place where they get now manufactured there. But yeah, we're successful.
So, okay, there, got that working. So there.
You got to pull the trigger, huh?
Yeah, was what I was hoping. So, I'm an Tree Faulkner, and I'm from Cal State, Channel Islands, and so basically I'm going to be talking about the data collection at the Atlas experiment. It's normally called the Trigger and Data Acquisition Group, and so to kind of give an overall idea of what this is about is from the detector we're getting the information every second, which is as mentioned earlier, like 1 petabyte a second, which is an enormous amount of data. And this is running for extended periods of time, so like 6, 7, 8 months at a time. And that's every second. So in order to find the new physics that we need, we have to sort through all of this and retrieve what we want. And so the first step of this is to be able to get the information we want. There's an online farm, which is the online system, which is basically going to take that data down and trim it down to about 100 to 400 bytes per second, which that's really small in comparison. So we want to be able to have certain techniques to retrieve the information that we want. The information that has like the Higgs boson, so we can look at it and be like, hey, we found what we're looking for. And even new stuff that we don't even know about. So it's, how do we get around this? And a lot of the data from it is spread across the whole world. Just different, there's data farms that just hold the data, and it just distributes it down to different tiers. And I believe Fresno has a tier 3 system that is going in, or has been. And so
it's being able to take the data from the detector and basically dispersing it throughout the world. And so that online farm, the first stage of getting the data, we call them triggers. There's basically one hardware implementation that is trimming the data down, and then there's two online systems, where it's just software that, it's a bunch of code that works through the data that's coming out of the detector. And so the goal is, once again, just to reduce that data down. And so they have to do a lot of tricks, basically, like figure out what to expect and then have it implemented. And so one of these that was in R&D and is starting to come out, the TDR report, the technical design report, was just approved, and they now have money for it. And it's a new trigger that they're going to be implementing, which is supposed to help tremendously in the whole process of this. And that's because the focus is on pattern recognition, which is recognizing what's going through the detectors, and then track reconstruction, which is a lot of the, we don't see like, oh, this is a new one that comes out. We have to calculate what it is. And this is through the detector of like different layers that can recognize particles going through it. And so the fast track trigger is a way that take these two elements and sort through the data. And it's an idea, about 60% of the CERN's resources right now is dealing with basically the track fitting, which is putting the tracks back together and figuring out what the particles are. It's estimated to increase the efficiency of this by 60%, which is a huge amount because they have to have the most advanced computing power there in order to handle everything. And this is done by using something called patterns, which it kind of relates to bingo, because in the detector we have a bunch of layers, and as the particles go through, it has like a signal saying, here's a hit, here's a hit, here's a hit. And so it's like, once it meets a requirement and says, we have a particle, let's save the information and send it onto the data farms where it can save the information. And so a little bit more about the patterns is there's different types of patterns. And these have different resolutions, so we have large patterns and thin patterns. So like characteristics of these is the large patterns have a high efficiency because they're allowed to record more particles that it's sensing. But that also increases like the amount of phase, like just noise from the detector and all that. But then we can have thin patterns which are smaller, higher resolution, so it reduces that. But it requires a lot more space to store this. So how we basically get a compromise of, well, which one do we use? There's a compromise. If we look at the efficiencies, so on the left is like large patterns where we can achieve this efficiency of like 90% by using 65 million patterns. But that's going to be a lot of fakes that we want. So in order to like look at the opposite case of this with the thin patterns, we require 500 million to achieve the same efficiency. And so this comes down to what should we do and how should we handle this. So there's a lot of simulations that go through this to estimate what's the best compromise of retrieving this data. And so what they have outlined for this is like the overall goal. They have a hardware limit that has been approved for budget, so they can make 16 million patterns. So they have to figure out the most efficient patterns to use for this. And so, but they want to keep that same efficiency as if they were using the thin patterns of having a higher resolution and the large patterns with the least amount of patterns. And so that's the overall goal right now, because since they've just gotten approved, they're now focusing on towards the optimization of this. And that was what I was working on, of finding ways of optimizing these patterns and being able to run simulations to pick out the ones that will benefit CERN the best, so we can reduce the computing power of processing this data. And so pretty much like an overall summary of everything was going through this. I learned C++, Python, and Root, which is really beneficial as a programmer. And the different types of algorithms that my supervisors had me look into of like, we have these characteristics, how can we sort through them? So I had to learn a lot about different like clustering algorithms of managing the data. And from this, I was actually able to give 2 working group presentations, which was really big, especially since the first one was the first presentation from the Fast Track Trigger Group. Because it just came out of R&D, they became a part of the Atlas program officially. So I was like the first introduction to the rest of the data acquisition teams that are working together. And so I have been invited to go back to work with the Trigger team next summer. And so just some pictures of the work that I was doing over at CERN, like being able to go down to the glider, and one of the presentations that I was able to give. And as was mentioned, we were able to travel on the weekends, which was really fun and beneficial. Being able to actually relax, because during that week it's non-stop work. And just want to give a special thanks, especially to Dr. Gao, who is in charge of this program, and from Channel Islands, Dr. Doherty and Dr. Ivana, for helping making it possible to go. All right. Thank you.
He already stated this, but what's the rate at which the collisions happen compared to how many collisions get put into the database? You know?
In terms of how many collisions per second to that, we look more towards how much data is coming out of it. So the collisions, I'm not too sure how many, but the amount of data per second is 1 petabyte. And what's being stored is about 100 to 400 megabytes per second. And so
this region, is at which level of the region? Is it level 1 or level 2?
the fast track trigger is going in between level 1 and level 2, so they're calling it 1.5 because it's a mixture of hardware components with specialized software of making it possible.
Yeah, so that's why you're not concerned with the region data, you're concerned with the data.
Yeah, so it's like the processors, as the data is coming through, it's like one of the first stages of the data coming through, so that like 1 petabyte, it goes through the fast track trigger, and then it's gonna trim it down tremendously, of like basically from the 1 petabyte down to like a terabyte, which would be 1,000 of the amount of data.
So that's gonna be an important thing, right? I mean, you're gonna knock that much data.
Yeah, and that's why it's kind of, they're really looking forward to it because they don't know exactly what to expect, but it's supposed to improve the efficiency tremendously.
Do you have any mechanisms for unexpected events and patterns to recognize them and study them separately?
They have the patterns stored in a way where they have a simulation that generates the patterns, and they, from previous data, to know what to kind of expect from it. So after running so many collisions, they figure out what are like interesting things that are happening and store it then, so it can get the data when it does happen to look at it separately.
Or if some new patterns appear, then they can always add it to the library.
Yeah, they plan to redo the simulations every few months from new data that they get as it runs. Yeah.
That was actually kind of, how do you ensure that you're not throwing away something interesting just because you don't know what to look for, right?
Yeah, and that's what
you did just a few events go through without filtering at all, just so you have some kind of background to check against, or?
Once in a while they do, but usually what they do is after running for such a long time, they take the most key parts that they found after observing it for years and years and store it so they can further get information on it. So they do have test runs every so often, like over the summer, every month there's TDAP week, which is they get control of the Atlas control room and run simulations and test all the hardware, unfiltered data, and know what to find. All right, and so pass it on. I don't know if this is gonna. Oh.
So was there anybody there that was disappointed you guys on the data? Anybody was, hey, I should have found something else?
No, they only have certain things they're looking for to give you time. I mean, that's sort of the issue, right? Is they have their understanding of how all this stuff works, so they look for what they expect to see if it's there, to see if their theory is true. So that's one of the issues is if they just collect random information, like they can look at it, but they're trying to test their specific theories usually. Is there a quicker? Is this working? Okay. So my name is Cameron Embry. I'm from Channel Islands. I'm a computer science and mathematics double major. I'm an undergrad. So I stole this slide from Graydon. But the only thing I wanted to mention on this slide is just reiterate the 1 petabyte per second. People have been talking about this a lot. It's a lot of information. And the reason that's insignificant is because Atlas itself, as was mentioned before, is generating about 10 petabytes a year that they save that gets distributed. But that's from the actual running of the detector. But we have our understanding of the physics, and we're testing the physics, and as we run the detector, we can start generating simulations of detectors. So that's what a event generator is, Monte Carlo event generator. We basically just run a virtual collision, and whatever the results are is supposed to emulate what actually happens in real life. But we have to run sort of the collisions first to understand all of it before we can do that. But the nice thing about Monte Carlo and Monte Carlo event generators is we can generate a lot more information. We're running these on servers. We don't have to wait for, well, first of all, we don't have to build the whole thing. But so it's just it's a way of collecting more information and testing more theories. One of the things, this says laser form, the center button. Okay. So where I sort of came in on some of the work that I did was dealing with these Monte Carlo event generators. We'll take a PDF function, which, okay, so PDF functions. So everyone has their acronyms in particle physics. A PDF function is a parton distribution function. I've also heard it called a parton density function, but whatever that is. So the point is, we use these things and they give us a probability of something happening. So it's sort of accounting for nature. So we have our understanding of how it works, but we still have to run the thing and make sure it does what we kind of expect it's supposed to do. And we can use the PDF with other mathematics to run things like determining a cross-section, which is the next slide here. But what I wanted to say, the one, sort of two things that I did. One was I tested software. It's an Apple Grid package, which is a new software thing that they're working on. It does a lot of different types of calculations, and I was just testing one of them. It's not out yet, but it's a really clever way that they have of structuring things so it doesn't take as long to run certain calculations. And then also, I created a class to do some generic PDF testing. You've seen this stuff before, so this is just a collision. The point is we want to account for nature. We want to know what our PDF is. In this case, we expect things to happen in a certain way, so we're looking to see if the things that are happening are what we expect. We have a theory, we're testing our theory. So, a cross-section. This, in Apple Grid, it was just called cross-section. They come up with cute names for some of these things, but this one's just called cross-section. But what would happen is they gave me, so Sherpa is a Monte Carlo event generator. I didn't deal with Sherpa. Someone else gave me a whole bunch of data and said, test my functions, make sure they're working. Because I think they're working, but I'm not sure. So they gave me, in this case, I had a total of about 46 million separate events. So those are like independent collisions in your virtual collider. And those took a long time to run, so it was about 50 minutes. I usually ran over some smaller amount of it because it's not reasonable to run something for 15 minutes every time I make a small change in my code. But I was just testing this function to make sure it works. I mean, that's what they need, right? They need programmers, not necessarily who know all the physics, but to test these things. I mean, because they can't just make it and assume it's going to work. So the Apple Grid project, before, a lot of the calculations they needed to do took a long time to run, like up to like weeks potentially on some of these things. But now they can reduce it down to like a lot less. And they do it by this really clever way of having a three-dimensional indexing table where they do their calculations beforehand, put them in their table, and then when they need them, they sort of index appropriately, as opposed to having to run multiple calculations each time they want something. So I got to work with, really work with, like the only guy who's working on this right now, Mark. I would meet like every day with him. So I'd have my laptop, he'd sit next to me, and we'd program together, you know, debug and try to figure out why things aren't working. And this is the guy who's like developing leading edge software, and I'm some kid from California. Like, so yeah, it's a great opportunity to work with some of these people. And also my advisor, Dr. Carly, as well. He was the head of the top group, which is actually a big deal, but that's not what I'm talking about here. This you're supposed to go ooh and ah on the left. So this is just one of the functions when we call it. The actual line itself in blue is from Apple Grid, and then my overlay is these like plus signs. Now, so the plus signs is because those are error bars. Don't worry about the error bars. Okay, what those are is Apple Grid has, again, a clever way of saving space when they run these calculations. And by saving space, they introduce some errors that go away when they run over lots and lots and lots of information. So they said, we're just not going to worry about that. We're just going to run over tons of stuff and it won't be a problem. But the point is they go away. This is just the best picture I have.
What's that x
Where? Sorry?
What is that x
In this case, I'm not sure on this particular one. part of the issue was I needed one that showed it working, and this one was one that was working. Some of the interesting things when you're testing stuff in programming is like, even if this one isn't doing what you expect, as long as, or excuse me, if it's not normalized the way you want to normalize something, so long as the other thing's not normalized the same way, they're both agreeing. So when you normalize them, they'll both agree again, but correctly. So in this case, I don't have this. The last thing I did, so this is just generic code improvement, so I consider myself a computer scientist first and everything else later. So I did a lot of coding to just general improvements. A lot of the issue is in computer science, you approach a problem, you develop paperwork on how you're going to solve the problem a particular way, and then you implement it. And a lot of this stuff, they say, we have a problem, here's the implementation. And we're like, well, what about the future? And they're like, we'll make that as we need it. So what happens is there's lots of different ways of implementing. So some of it's in C, some of it's in C++, C is in C++, but the point is there are different paradigms of coding. Some of it's more and less efficient, so I went through and just sort of cleaned it all up. There was lots of code, so. And then the last thing I did is I introduced a new class, which was part of the thing that my advisor was working on. He's part of interfacing to this Apple Grid software to make it more efficient. It's an easier interface to use, so he's developing sort of the user end of it. There's lots of different PDF functions that you can use, and they're all slightly different, and where these functions come from is they run the collider and they sort of figure them out. It's sort of accounting for nature. But because we're figuring them out from running the collider, any errors that are in there, something that we didn't account for, we're saving as being worthwhile information when it might not be. So the interesting thing is that actually Atlas's one that they use for their simulations is the least accurate towards the actual results they get from running their collider. I mean, not by very much. This is the ratio of just a couple of them. But my advisor's like, this is a big deal. You don't know why this error is here, and no one wants to talk about it. In fact, he was talking to me about it. He's like, I was just talking to some dude yesterday. No one wants to deal with this issue. They can sort of get rid of it by running over lots and lots of events, but he wants to publish a paper on this and stuff. So I developed a class that would allow for next summer I could work on that, or someone else I could take that and test various PDF functions. So the last thing is just that I wanted to say, you get to learn a lot of different types of coding. You get to contribute meaningfully to like a project. We got to visit the Apple's Cavern, that's been mentioned a bunch of times. And then also you can get invited back. The interesting thing about the Apple Grid software is that that's ongoing, so when they're ready to publish it, like I could get my name in that paper and that would be super cool. It looks good for the CSUs, it looks good for me. So you get to contribute. This is my advisor who's a really cool German guy. But we really work like every day together. This is me in the cavern like normal. Again, the summer student lecture series. We did some traveling on the weekends, so there's Lake Geneva, went to Venice, of course. Braden and I went to Berlin, and then of course, France, we had a visit. So thank you very much. The only things I want to make sure is I thank Dr. Gao, the people at Channel Islands, and miscellaneous funding groups, because we really couldn't get all the way over there and do this if we didn't have that. Thank you. Questions? We're almost out of time, so I wanted to get Jimmy up here. Okay. Yeah.
Hi, I'm actually Jimmy Gonzalez, and I'm from the school here. You may know about it or not. It's just a general outline of what I want to talk about. I will go through that. But before quarks were discovered, it was thought that protons and neutrons were the fundamental building blocks of matter. But then suddenly it was discovered that that wasn't true. There were leptons, quarks, and other vector bosons, which I won't get into right now. And this here is the Higgs boson, which is thought to give matter mass. And these are just some of the discoveries by American physicists or US physicists. You can see here the dates, and actually almost all of these were discovered by US physicists.
what collider it
I'm actually not sure. They're all over the world.
was. Geez, yeah. Wait
And here are just some of the masses for the leptons and the quarks. And you can see here that the top quark is actually the most massive, which also makes it very interesting since it's even heavier than the recently discovered Higgs boson. And as you can see here, it's more than 20 times more massive than neutrons or protons. And the thing that makes this interesting is that it fragments. Well, actually, it doesn't fragmentate. That doesn't mean it doesn't form other particles. So what happens is that it decays before it becomes paired to another particle. And so you can kind of get like a bare quark, which is very rare. And to create these top quarks, well, it's actually very tricky. So what we get two cars and we accelerate them close to 40 meters per second. It's very difficult. Well, not quite. Instead, we make miniature Big Bangs. And this is actually a top event, so you get protons coming in, and then they collide. Well, it's not really, well, they collide. I want to get into the one anyway. So you get a top and anti-top pair. And then those particles decay into a boson and bottom quark. And this here are, when the boson decays into two hadrons, the hadrons decay and then they create a jet. So this here is a hadron decay, and this is atomic decay, and these are leptons. And so the detector, as he was describing and such, we don't actually measure the top quark or the bottom quark or any of the subsequent quarks. Instead, you get just a spray of other particles like muons, photons, electrons. And so my job was to actually reconstruct this top quark. And this is just a general procedure of that reconstruction. We get a clustering algorithm to make jets. We match the jets to particles, and then we identify those particles to the jets. So here you can see these that we came to two quarks, and then from two jets, just a spray of particles that are just collimated. And so we can just get a cone of these particles when we just cluster them. And this has some radius, not very important. And the next step is to actually match those particles to the jets and identify what they are. So here you have some particle, it decays into jets. And then since particles have some lifetime, they do move or they displace some distance before they decay into other particles. And so you get these displaced tracks. That's why there's little dash line there. But it's not so easy as I just explained, since you have well, theoretically you have these calculations, these Feynman diagrams. But what we actually measure are this mess. You have background radiation and other events. That's not really a collision, it's more kind of they pass by each other and it creates photons. That kind of makes this kind of messy. So some of the tools that we actually use at Atlas, or use all the C programs, Python, and I think you've heard of. And this here's a histogram. What it is, it's some, in this case it's mass and frequency. And this little resonance peak is the Higgs boson. And what I was actually doing was using actual data and event generators, since event generators can actually create a more controlled environment, change parameters like whether some particles interact and how strong that interaction is. So we kind of just test your models with event generators and then go to the raw data. And then something messes up and you go back and just cycle through that. So my actual project was to optimize the reconstruction, minimize the uncertainties, since there's a bit of competition between CMS and Atlas, two groups. Since CMS actually had better measurements, but they also had large uncertainty. And most of the uncertainty was kind of all the assumptions that they made. And this is actually histogram is the frequency, this is the mass down here. And in red is the actual, or you can think of it as kind of the theoretical distribution for the top. This blue line is the one that I made. It's slightly better than the one that was before. And the point here is that when you actually measure the water peak and the width here, it's actually closer to the theoretical value. I have more plots, but I wasn't able to put it in here for the transparency, sorry. And in fact, I forgot to mention one thing. Here what we're doing is kind of the analogy of the car. Is that the car had like glass pieces, tires flying everywhere. We'll look at the tires, the glass pieces, and engine parts, and try to figure out the make and model of that car, which is, as you can imagine, not so easy. And here are just some of the things that I learned and accomplished. I learned a lot about, well, quantum chromodynamics and all this other complicated physics. And I was actually working with several advisors and all these other physicists, and since I would ask my advisor a question, he sent them their note. So I would either look it up myself or email someone else. And if they had an answer, I would go walk all the way to their building, speak with them for about a few hours, get an answer, then have a question for them. They wouldn't have an answer. So they'll send me to another person, and they'll send me back to my advisor. And I'll just do that a couple days, for a couple days until I kind of start getting results. And apart from working from that, also explore European culture. This is the Science Dome in front of CERN. This is Geneva. This is a famous jet. You can also think about jets as in cargo jets. Venice, Paris, and my little office here.
We got a window.
Yeah. And thanks to these people for making this happen.
My only comment was I wish I was a graduate student, yeah, I get to go. Pretty awesome. Yeah, like you said, go to a different building and ask somebody, go ask somebody else, and that's pretty awesome.